Hello students, welcome to this lecture number 7 on state of matters. In this lecture we will be again going to discuss a very important topic, that is the kinetic molecular theory. So today's lecture we are going to spend time on discussing the kinetic molecular theory. If we are going to discuss this topic, let us have some discussion what we have discussed in our previous 5 lectures. In the first lecture we have discussed about the introduction to the state of matters chapter, that is we have discussed about the different types of forces, attractive forces, that is molecular attractive forces, and then we have discussed about how there is a 3 state of matters that we have discussed. It is basically the balancing between the 2 forces, 2 energies, and if you want to know more about it, you should visit these lectures. The second lecture we have discussed about the gaseous state and its characteristics and 2 different laws, that is the Boyle's law and the Charles law. In the third lecture we have discussed again different law, 2 different very important law, that is the Hamilton's law and the Avogadro law. In the fourth we have discussed when we combine the 3 gaseous law into one, it will become say ideal gas equations, and we have discussed and discussed. Then we have discussed about in the 5th lecture, that is the Dalton's partial pressures law, that we have discussed in the 5th lecture, and in the 6th lecture we have discussed about the Graham law of diffusions with different types of numericals. If you have not watched this lecture, you must see it, and I am 100% sure that you are going to benefit out of this. So in this lecture we are going to discuss again a very important thing in the state of matter chapter, that is the molecular kinetic theory of the gas. Molecular kinetic theory, kinetic molecular theory, or molecular kinetic theory of the gas. This is Nikhil Mukherjee in the Science with Mukherjee Sir YouTube channel. So let us understand why there is a theory that comes into play. It is basically, you can see that Boyle's law and Charles law are basically the concise statement of an experimental facts. And when any experiments establish any observation, then there is a curiosity grows among the scientists to know further what is going on in the molecular level. As for example, from the experiments of the Boyle's experiments, Boyle's law, that we are able to understand that when we compress the gas, the pressure of the gas will increase. And now question arises, when we compress the gas and the pressure of the gas has been increased, what is going on the molecular level? And that has been answered by framing a theory that is called the kinetic molecular theory, and it will deals with all those things that we cannot able to see, that is molecules and atoms. So it is also called the microscopic description of the behavior of the gaseous law. So what are the postulates? Let us understand. Postulates are basically the first number postulate that gas is made up of a large number of particles, and these particles are called the molecules. And for a particular gas, the molecule have identical in terms of its mass and in terms of its size, but for the different gas it will have the different things. So it's the first postulate, the gas is this is the first postulate that we have already discussed, that is the gas is composed of large number of particles called molecules, and for a particular gas molecules are identical in terms of size and mass. Second postulates, as you can see, the distance between the molecules are very high. So we can consider the volume of the molecules are negligible in compared to the vacant space between them. And this postulate supports the fact that gas is greatly compressible. Gas can be easily compressed. That is the one of the physical parameters that we understand, that we have discussed in the lecture number 2, that gas is compressible. And why it is so? Because there is a lot of gap between the molecules, and the molecules we can consider as a point mass, or we can consider the volume of the particle is negligible. So this will prove the compressibility of the gas. Compressibility of the gas. Then the third postulate, this is the third postulate. You can see that as the distance of separation between the molecules are very high, the attractive force between the molecules are very negligible. We can say that there is no attractive force between the molecules, and this supports the idea, the expandability of the gas. Gas can expand. Gas can expand. It can expand to the available volume, and that proves that there is no attractive force between the molecules of the gas. Fourth point, that gas in the gas particles, whether it is moving or it is stationary, it is said that gas molecules are moving. Gas molecules are moving randomly, and the gas molecules are not stationary. If it is stationary, then what is going to happen? Its position will be fixed, and if its position is fixed, at that time the shape of the gas will be fixed, but that is not practically observed. We observe the gas do not have any shape or do not have any volume. That what you observe in case of your solid. In the solid, the position of the molecules is fixed, but in case of gas it is not fixed because it is moving. That it proves that gas molecules are moving randomly at any direction. We can write at any direction. Okay, now that is the fifth. Fifth is the gas molecules are moving very fast at any directions. Gas molecules are moving very fast at any directions. We can write this. With each other and with the collide with other molecules, or wall of the container in which it is kept. So gas molecule moves randomly at any direction at a straight line, and it will collide with each other and also collide with the pressure, and that is why gas exact pressure in every direction. In the physical property of the gas, we can also discuss this point that gas can exact pressure at any direction, and this is the reason because the gas molecules are very fast and it moves randomly at any direction at a straight line, and when it collide with the vessel surface, it will create the pressure. So this is the fifth postulate, that is very important postulate, and it gives that why gas exact pressure. Gas exact pressure, due to this fact, it collides with the wall of the container. Okay, this is the fifth. This postulate says that gas molecules are elastic in nature. Gas molecules are elastic in nature. So when it collides with each other or collides with the walls, it will always create a elastic collisions. That means there will be no loss of energy. Energy may be transformed from the one molecule to the others, but the energy will be fixed at any time. There will be no loss of energy. So we can say the collision, molecular collision of molecules, are elastic in nature. Elastic in nature, and no loss of energy is observed. No loss of energy. And if there is a loss of energy, what is going to happen? After some time, the gas will be settled down. But that is not going to happen. So the collision, the molecules are elastic in nature and they are impenetrable and very hard and rigid, and collision of the molecules in the walls and with themselves are the elastic in nature, and there is no loss of energy, and energy is fixed. We can say energy is constant, no change. Only it will change when we change the temperature. Seventh postulate, as we can understand, that there is a collision between the molecules. Naturally, the one molecules will not have the same energy, same velocity. The velocity goes on continually changing, and but velocity is changing. But there you can prove that distribution of the velocity is fixed, and that is depend on the temperature, and that we are going to discuss the Maxwell distribution. So we can say velocity of molecules are changing shape. And 8 point, the kinetic energy of the velocity, kinetic energy of the molecules. Kinetic energy of molecules are also changing, changing. So when we are talking about the kinetic energy of the gas molecules, we will always indicate, we always say that will be the average kinetic energy. Average kinetic energy. And this average kinetic energy, we will prove it that it is directly proportional to the temperature. If the temperature change, then it will change. So you understand, this is the postulates for the kinetic molecular theory. And from this postulate, we are able to elucidate, we are able to discuss, explain different types of behaviors of the gas. Why gas is compressible, why it is expandable, why gas do not have any exact volume or exact shape, why gas exact pressure, why with the increasing the temperature the gas pressure is increasing. That we are also going to understand from this postulate. Now we are going to understand the distribution of the velocities. As you can see, the velocity of the gas molecule that keeps on changing. It is not a constant affair. It will keep on changing, but the distribution is fixed, and that we will understand from the Maxwell distribution of the velocity. If we plot the velocities of the molecules as against the fraction of the molecules, that is the fraction of the molecule, fraction of molecules, that is being represented by dN by N, and this is velocity. For a particular temperature, this distribution will be like this. And here you can see there is a maximum proportion, that is, suppose it is F1 and this temperature is T1, and this velocity is called the alpha 1. Suppose this velocity is called the most probable velocity. This velocity is called most probable velocity. Most probable velocity, and it is represented by alpha, and also you can represent it by C star. This is called the most probable velocity. Why it is called so? Because we can observe that for a particular temperature, the fraction of the molecule, this fraction of the molecules, maximum fraction you can say, will have this velocity. Maximum fraction of the molecules will have this velocity, and that is why it is called the most probable velocity. The most probable velocity, we can write the definition. It is the velocity. It is the velocity possessed by the maximum fraction of molecules. Maximum fraction of molecules. And this is represented by alpha, or it is also represented by C star. This is most probable velocity for at a particular temperature. We also write at a particular temperature. At a particular temperature. So here is the temperature T1. This velocity, this distribution, Maxwell distribution of the velocity found. But if we change that, increase the temperature, this velocity will be like this. And this will be T2. Where T2 is greater than T1, and you can observe the most probable velocity, the fraction is decreasing. The fraction of the molecules having this amount of velocity is decreasing, and it will be T2. And here you can write that T2 is greater than T1, whereas alpha 2 is greater than alpha 1, and the fraction of the molecules, that is F1 is greater than F2. So when we are increasing the temperature, the velocity, most probable velocity is increasing, but their proportion of the molecules that goes on decreasing, that we can easily see from this distribution. This is called the Maxwell distribution of the velocity, and from that you can understand the velocity of the molecules at the gaseous phase. But to explain the things that we will study in the higher class, we need to have some other velocities also that we are now going to discuss. That is the one most velocity, and second is the RMS velocity. RMS means root mean square. Root mean square velocity. This is RMS velocity, root mean square velocity, and it is represented by U or C. What it is? So it is basically the square root of the mean of the square of the velocities is called the root mean square velocity. So you can see U is equal to, you can write V1 square plus V2 square Bn square, and it is square root, and in the denominator you will find n. This is the root mean square velocity. So you understand most probable velocity, and it is RMS, the root mean square velocity. Okay, velocity, that is the average velocity. Average velocity, and it is represented by V, and it is the average. It is the average of different velocities, of different velocities of molecules. A molecule do not have the fixed velocities, right? After the collision, its velocity will change. Again after a collision, its velocity will change. So it is the average velocity that is been represented by V, and it is V1 plus V2 plus V3 plus divided by N. This is called the average velocities. So we understand three types of velocity. One, that is the most probable velocity, another, that is the RMS velocity, and average velocity. Now, is there any correlation between all those velocities? Yes, there is a correlation that we are going to understand. For most probable velocity, it has been deduced that it is 2RT by M. R is universal gas constant, T is absolute temperature, M is the molecular mass. Then the average velocity is given by, this is very important formula that you have to remember, RT by M. This is for average velocity. And another, that is the RMS velocity, that is the most important thing. RMS velocity, it is the 3RT by M. Now, if we make a correlation between these, we will find alpha, that is most probable velocity, by the RMS velocity, it will be coming around 816. Whereas, in case of, this is U means the RMS velocity. U is RMS velocity. U. Okay. Now, average velocity by RMS velocity, it is coming around 261. 0.961. So, from this you can able to understand the RMS velocity is much more higher than the other two. So, if we take the ratio of the most probable velocity, average velocity and RMS velocity, we will get this ratio 1 is to 1.128 is to 1.228. So you can easily understand the velocity, most probable velocity is less than average velocity less than the RMS velocity. So do we understand how this average velocity, different types of velocity in the molecules of the gas is been designated, is been denoted. Now we are going to discuss another, that is the kinetic gas equation. Kinetic gas equation. It is been this PV 1 by 3 mn u square, whereas P is the pressure, V is volume, M is mass of individual molecule, and N is the number of molecules, and U is the RMS velocity, root mean square velocity. So from this you can able to derive the correlation between the kinetic energy with the temperature. What we will do? This will, you can write m u square. M is where the mass of the gas, because this is the mass of one molecule and the total number of molecules n. So it will be the mass of the molecules. So we can write this again, 2 by 3 half mu square, and this mu square is basically the kinetic energy of the gas. So we can write PV is equal to 2 by 3 Ke, kinetic energy. So this can be further written, Ke is equal to, we can written, that is 3 by 2 RT. So kinetic energy, you can see, you can understand that it is kinetic energy of 1 mole of gas is this, and it is directly proportional to the temperature, right? Because this is the constant term, and if we go to understand the kinetic energy for the molecules, it will be what? And it will be this R divided by N. N is Avogadro numbers into T, and we can see 3 by 2 K into T. And here K is the Boltzmann constant. K is Boltzmann constant. So we are able to derive the kinetic energy of the gas of the mass M and the kinetic energy of the molecules. And we understand this, it is directly proportional to that temperature. Now question arises, which type of questions is going to come, that I am going to discuss now. This question that we are going to discuss, AIIII 2010 में this question has came. The question is, for a particular gas velocity proportional to absolute temperature, square root of absolute temperature. This is the question, that for a particular gas, velocity is directly proportional to absolute temperature, inversely proportional to the absolute temperature, directly proportional to the square root of the absolute temperature, and inversely proportional to the square root of the absolute temperature. So we know the average velocity is, this is the formula, 8 by pi RT by M. So RT here these are constant, so we can write this, V is square root of the absolute temperature, directly proportional to the square root of the absolute temperature. So directly proportional to the square root of absolute temperature, it will be correct, and it will came in the AIEEE in 2010 exams. So this type of question will ask, and you have to answer this. That is all for today's lecture. I hope you understand all the things that we have discussed. That is the kinetic molecular theory. Kinetic molecular theory is what? That will postulates a mental map by which we can able to answer, we can able to explain many happenings, main behavior of the gas, and this type of question will asked in the questions. So it is very simple, but you need to understand it very properly. And the next lecture we will be going to discuss another very important topic that we will discuss in the next. Okay, thank you very much for watching. Thank you.